Conditions exist in any transmission and distribution system that result in power losses, both in the systems and equipment that deliver power and in the systems and equipment that use power. To reduce or compensate for such losses, utilities often use devices such as capacitor banks and shunt reactors. In addition, events sometimes occur that create excessive current in the T&D system. Excessive current can damage system equipment and create hazards for personnel. So utilities may use series reactors to protect equipment and personnel from the effects of excessive current. In this program, we're going to look at the function of substation capacitors and reactors, and we'll see how to safely clear them, maintain them, and test them. Because of the nature of electrical systems, some of the power that is produced at a power plant is not usable by the consumer. To a utility, unusable power represents lost revenue. To minimize losses, utilities try to reduce the amount of power that is unusable and increase the amount that is usable. They sometimes do this with substation capacitor banks and shunt reactors. In this part of the program, we're going to look at conditions that cause power to be unusable, and we'll look at how a capacitor bank and a shunt reactor compensate for those conditions. The primary purpose of a power plant is to produce usable power, which we'll call working power. Working power is voltage and current that perform work. A key factor is what the current is used for. Some devices use nearly all of the current that they draw to perform useful work, such as the current that is used by incandescent lights, or the current that is used for resistance cooking. However, some of the power that is produced at a power plant does not perform useful work. We'll call this power non-working power. Non-working power is voltage and current that do not perform work. Again, a key factor is what the current is used for. Some devices do not use all the current that they draw to perform useful work. For example, an induction motor needs a certain amount of current, called magnetizing current, to create a magnetic field in the motor. The magnetizing current does not perform work. Only after the magnetic field is created by non-working magnetizing current can working current operate the motor and perform work. Transmission lines also need a certain amount of current that does not perform useful work. The current needed to charge the lines, called charging current, does not perform work. Long, high-voltage transmission lines may draw a lot of non-working charging current in order to deliver working power from one location to another. The power in a transmission and distribution system generally includes both working power and non-working power. The relationship between working power and non-working power determines the efficiency of the power that is produced. We can show this relationship using a simplified illustration. In this illustration, working power is represented by the horizontal line. Working power is measured in watts. Non-working power is represented by the vertical line, and it's measured in VARs, which is volt-amperes reactive. Non-working power may include two different and opposing conditions. One of these conditions is represented by the upper half of the vertical line. This condition is non-working power that is a result of charging current, such as the charging current required to energize long, high-voltage transmission lines. This kind of non-working power is referred to as capacitive power. The lower half of the vertical line represents a condition that is the direct opposite of capacitive power. This condition is non-working power that is a result of magnetizing current, such as the magnetizing current required by induction motors. This kind of non-working power is referred to as inductive power. Both capacitive power and inductive power may be present in a T&D system at the same time. If they're equal in value, they will cancel each other out, leaving only working power. The effect of this relationship can be shown using another simplified illustration. This illustration is a bird's eye view of a wagon that has 3 horses hitched to it. The goal is to perform work efficiently by moving the wagon in a straight line from left to right. To relate this illustration to a T&D system, we'll let the horse at the right represent watts, or working power. The horse at the top of the illustration represents capacitive VARs, or non-working capacitive power. And the horse at the bottom represents inductive VARs, or non-working inductive power. If the top horse and the bottom horse pull with equal force, they will cancel one another's efforts, and the middle horse will be able to pull the wagon to the right in a straight line. Relating this to a T&D system, if non-working capacitive power and inductive power are equal, they will cancel each other out, leaving only working power in the system. Now, suppose that there is less capacitive power in the system than inductive power. The capacitive power will only cancel an equal part of the inductive power. The remaining inductive power, together with the working power, will move the wagon to the right and down. Work is being performed, but not as efficiently as when the capacitive power and inductive power are completely canceled out. The power that a utility has to produce to meet the demands for both working power and non-working power is called apparent power. Apparent power is measured in volt-amperes and is represented in this illustration by a diagonal line. When a T&D system has more inductive power than capacitive power, the result is apparent power on the inductive side of working power. If a T&D system has more capacitive power than inductive power, the result is apparent power on the capacitive side of working power. The ratio of working power to apparent power is commonly referred to as the power factor. Capacitor banks and shunt reactors are used to improve the power factor, to improve the ratio of working power to apparent power. Power factor can be expressed as a percent or as a decimal number. For example, if working power is 80 watts and apparent power is 100 volt amperes, the power factor would be 0.80, or an 80% power factor. The ideal condition is achieved when apparent power is the same as working power, for a power factor of 1, or a 100% power factor. This ideal condition is called unity power factor. However, in actual practice, a T&D system is seldom at unity power factor. For example, in today's power systems, it is common for the combined effect of many motors to create an excessive demand for non-working inductive power. Excessive demand for non-working inductive power results in a lower power factor than is desirable. In other words, the utility has to provide more power than is actually needed to perform useful work. However, rather than increase power output, power factor can be improved by using capacitor banks to offset the excessive demand for inductive power and bring the power factor closer to unity. Another condition that is becoming more common in some power systems is an excessive demand for non-working capacitive power due to longer and higher voltage transmission lines. Excessive demand for non-working capacitive power also results in a lower power factor than is desirable. Rather than increase power output to meet the demand for capacitive power, power factor can be improved by using shunt reactors to offset the excessive demand for capacitive power. In a nutshell, capacitor banks and shunt reactors are used to improve the power factor of a system, to reduce the amount of non-working power in the system, and as a result, increase the amount of working power that is available. Capacitor banks are used to offset excessive demands for inductive power, and shunt reactors are used to offset excessive demands for capacitive power. Now, in order to perform reliably, Capacitors and reactors require occasional maintenance. In the next several parts of this program, we'll concentrate on capacitor banks. When we return, we'll start by looking at how to safely clear capacitor banks for maintenance. In this part of the program, we're going to look at how to clear a capacitor bank for maintenance. The main steps are pretty much the same as for clearing any device in a substation. These steps include de-energizing, isolating, testing for dead, and grounding. However, a capacitor bank is different from other devices in a substation in that it stores an electrical charge even after it's been separated from its source of energy. So, in addition to the main steps to clearing a capacitor bank, we'll also look at some special safety precautions that are required. This simplified illustration will help show the general principles of de-energizing and isolating a capacitor bank. The illustration includes an energized three-phase bus, a three-phase circuit breaker, 3 single-phase disconnect switches, and a three-phase capacitor bank. Very simply, a capacitor bank is de-energized by electrically separating the bank from its source of energy. In this example, the bank is de-energized by opening the circuit breaker. A capacitor bank is isolated by physically separating the bank from its source of energy. In this example, 3 single-phase disconnects are opened to provide a visible break between the source of energy and the bank. The actual switching devices that are operated and the sequence in which they're operated varies with the design of the substation. Normally, a capacitor bank is switched out only after getting permission and detailed switching instructions. Then, after the capacitor bank has been de-energized and isolated, it's good practice to test the capacitor bank for dead. Here, a worker is making sure that a glow stick works on a circuit that he knows is energized before he uses it to test a capacitor bank for dead. The tube lights up, indicating that the circuit is energized and that the glow stick is working. Next, he tests each phase of the capacitor bank. If the tube doesn't light up, it indicates that the bank is not energized by an AC source. It doesn't tell whether or not there is a charge remaining in the bank. After testing the entire bank, the worker rechecks the glow stick on the known live circuit to make sure that the glow stick is still working reliably. Normally, with other substation equipment, the next step would be to ground it. However, with a capacitor bank, it's important to wait a while before grounding the bank. Typically, the waiting period is 5 to 10 minutes, depending on your company's requirements. The waiting period is necessary because the capacitors will hold a charge for a period of time even after they've been separated from their source of energy. This stored charge can be very dangerous. The potential hazard can be demonstrated with a small capacitor that is commonly used in electronic components. This capacitor was energized, and then the source of energy was removed. If the terminals of the capacitor are shorted together, the charge in the capacitor is released rather violently, and this is a small capacitor compared to the capacitors used in substations. Substation capacitors, like this one, can store thousands of volts. Does this mean that when you ground a capacitor bank, you're going to have a violent discharge of energy? The answer is no, and here's why. Substation capacitors are typically built with internal discharge resistors, like this. When the capacitor is separated from its source of energy, the resistor bleeds off residual voltage. Generally, the resistor is supposed to bleed the charge down to 50 volts or less within 5 minutes. The 5 minutes is important. As a general rule, you should wait 5 to 10 minutes after de-energizing and isolating a capacitor bank before grounding it. That way, when the bank is grounded, there should only be a minor discharge to ground rather than a violent, potentially damaging discharge. So after a capacitor bank has been tested for dead, and after waiting 5 to 10 minutes, the bank can be grounded. The basic ground connections are generally the same from bank to bank. The first connections are to an established ground. The next connections are from the established ground to the neutral side of the bank. The last connections are from an established ground to the normally hot side of the bank. The exact placement of portable grounds on a capacitor bank can vary with the design of the bank. What's important is to find out how the capacitors are connected together before determining where to place the grounds. For example, this bank is actually two banks in one. The three lower tiers of capacitors make up the three phases of the first bank. The three upper tiers make up the three phases of the second bank. The source to the capacitor bank is connected directly to a bus for each lower tier of capacitors. The normally hot terminal of each capacitor is connected to the bus by a fuse. The source is also connected to vacuum switches, which are opened and closed to connect the upper tiers to the source or disconnect them from the source. The neutral terminal of each capacitor is connected directly to the frame of the capacitor bank. The frames for the three lower phases of the bank are connected by conductors. The frames for the three upper phases are connected together in the same manner. To safely ground any capacitor bank, several connections are made for each phase of the bank. The first connection is always to an established ground. Here, the established ground is a station ground. This worker makes a habit of connecting all of the portable grounds that he'll use to ground the bank to station ground before making any other connections. That way, when he connects a portable ground to the bank, he knows the other end is connected to an established ground. After making the connection to an established ground, the next connection is usually to the neutral of the capacitor bank. For this bank, the neutrals for the lower tiers can be grounded by attaching the portable ground to one of the conductors that connects the frames together. The neutrals for the upper tiers of capacitors are grounded the same way. Next, the source, or normally hot side, of each tier is grounded. For the lower tiers of this bank, this involves applying grounds to each of the three single-phase source leads that connect directly to the lower tiers. A ground is also applied to the lead between each vacuum switch and upper tier. With a vacuum switch, there is no direct, visible evidence that the switch is closed. If the switch were open, the upper tier would not be connected to the grounded source lead. Applying a ground between the switch and the upper tier ensures that the upper tier is grounded even if the switch is not closed. The number and placement of grounds on a capacitor bank can vary. There are many different ways that the capacitors in a bank may be connected together, and you have to be very careful that the grounds you place connect every portion of the bank to ground, such as the additional grounds needed in the example we looked at to ground the upper tiers of capacitors. Now that we've looked at how to ground a capacitor bank using portable grounds, you also need to be aware that portable grounds are not always used to ground a bank. For example, here's a bank that is equipped with switches. The bank is grounded by closing the switches rather than by attaching portable grounds. In addition to the switches, this capacitor bank also has a safety interlock system. Part of the interlock system is a security fence that is normally locked. The other part is a key to the gate of the security fence. The key is normally located in the gearbox mechanism of the switch that isolates the capacitor bank. The key cannot be removed from the gearbox mechanism until the switch is opened. This helps to ensure that the capacitor bank is de-energized and isolated before the gate can be opened. As with any other capacitor bank, the 5 to 10 minute waiting rule should be observed before the bank is grounded. To ground this bank, the first switch that is closed is a master ground switch. Closing the master ground switch grounds the frame of the capacitor bank. The neutral terminal for each capacitor is connected to a conductor, which is connected to the frame of the capacitor bank. So grounding the frame effectively grounds the neutral of each capacitor in the bank. Next, shorting switches are closed. The hot side of each capacitor is connected to a bus. Closing the shorting switches simultaneously shorts the bus to the frame and grounds the hot side of each capacitor. In this part of the program, we looked at a couple of capacitor banks. It's likely that the banks in your system are different from these and from each other. Therefore, it's important that you familiarize yourself with a given bank so that you know what you're working with. And it's important that you follow the basic principles for clearing a bank. These principles include de-energizing and isolating the bank, waiting 5 to 10 minutes, then testing the bank for dead, grounding the neutral side of the bank, and grounding the normally hot side of the bank. Only after a capacitor bank has been safely and completely cleared and grounded can you go ahead with maintenance. We'll look at some common capacitor bank maintenance tasks when we continue in the next part of this program. Maintenance tasks for substation capacitor banks are pretty much the same, regardless of what bank you're working on. We're going to look at some of the more common maintenance tasks, including inspecting and cleaning capacitor bank components and replacing fuses and capacitors. We'll also look at special precautions that are required when handling capacitors that contain PCB insulating fluid. Capacitor bank maintenance is commonly scheduled at specific intervals, depending on company policies. The general purpose is to look for any conditions that could cause a failure in the future. Failures more commonly occur at individual capacitors and capacitor fuses. Typically, both are visually inspected on a regular basis. Each capacitor in a bank is protected by a fuse. If a disturbance occurs that might damage the capacitor, or if the capacitor fails, the fuse should blow to disconnect the capacitor from the bank. During an inspection, the fuses and fuse connections are checked to make sure that they are not loose, frayed, or corroded. If any part of a fuse or its connections appears to be deteriorating, it's better to replace the fuse than to wait until it blows. The capacitors are also thoroughly inspected. Common problems to look for when inspecting capacitors include broken, cracked, or chipped bushings, leaks, or signs of leaks, and bulging or other signs of damage. If a capacitor shows any of these problems, it may need to be replaced. In addition to the fuse connections, all other electrical connections in the capacitor bank are checked to make sure that they're not loose, frayed, or corroded. These include connections to the capacitor terminals, connections from the source to the bus of the capacitor bank, and connections to the frame of the capacitor bank. Loose connections should be tightened. Corroded connections should be cleaned or replaced. Other items that should be cleaned are all the insulators in the bank, including the frame insulators, bus support insulators, and capacitor bushings. Dirt, greasy film, salt deposits, and other contaminants from the air can accumulate on insulators and reduce their ability to insulate. If the capacitor bank is equipped with shorting and grounding switches, each switch should be checked. A precaution is needed here. Before doing any work on a switch, connect jumpers across its connection points to ensure that the bank remains grounded while the switch is being serviced. The movement of the switch is checked to make sure it opens and closes without binding. While the switch is open, the connecting surfaces are checked to make sure they're clean and free of corrosion. If necessary, the surfaces can be cleaned with a rag and an approved solvent. Any burrs on the surfaces can be removed with a file. While the switch is closed, the connecting surfaces are checked to make sure that they make good, firm contact. The main purpose of capacitor bank maintenance is to prevent failures. But even with maintenance, some failures are going to occur. So many times when you work on a capacitor bank, it will be to replace blown fuses and failed capacitors. Capacitor fuses can blow for any number of reasons. For example, fuses can be blown by excessive current from switching. Another cause of blown fuses is animals such as squirrels, birds, or snakes getting into the bank and short-circuiting a capacitor. Sometimes a fuse blows because the fuse link was weakened by fraying. And there's always the possibility that a blown fuse is caused by a capacitor that failed. When it's obvious that a failed capacitor caused a fuse to blow, as is the case here, both the fuse and the capacitor are replaced. When a fuse is blown, but the capacitor appears to be normal, it may be necessary to test the capacitor to determine if it is good or not. We'll look at testing capacitors later in this program. Before working with a capacitor that has a blown fuse, it's very important to short the capacitor terminals together with an appropriate shorting device. The short is needed because the blown fuse disconnected the capacitor from the source bus before the bus was grounded. As a result, the capacitor may still contain a charge. As an added precaution, a short should be applied from the capacitor tank to the shorted terminals. This protects against a discharge resulting from an open inside the capacitor. The effect of an open can be shown using a simplified illustration. This illustration of a capacitor includes two terminals, a bleed resistor, and a number of capacitive elements in series. If an element inside the capacitor opens, the open may prevent the capacitor from completely discharging when it is shorted and grounded. When the capacitor is moved, the opened elements inside may reconnect and allow the remaining charge to reach the capacitor terminals. Shorting the terminals to the tank will prevent a harmful discharge if an open happens to reconnect when the capacitor is moved. Other precautions may be necessary depending on the condition of the capacitor that is being replaced. For example, a bulged capacitor should be handled with extra care. A capacitor bulges when arcing in the insulating oil creates gas and increases the internal pressure of the capacitor. An inadvertent bump may break the bushings or rupture the capacitor, allowing pressure to escape forcefully and possibly causing injuries. To protect the capacitor from bumping while it's being removed, it can be wrapped in rags. Finally, special precautions should be taken when working with a damaged capacitor that contains PCBs. If a capacitor is not labeled, assume that it contains PCBs and observe the appropriate precautions. Generally, appropriate precautions include wearing approved protective equipment, such as a protective suit, boots, gloves, and eye protection. When the damaged PCB capacitor is removed, it is placed in an approved container until it can be properly disposed of. Any equipment or structures that were contaminated with PCBs must be cleaned. Here, a cleaning agent is being poured over portions of a contaminated capacitor bank to rinse off PCB fluid that leaked from a bad capacitor. Then, the affected parts of the bank are thoroughly wiped down. An absorbent material is spread on the ground to absorb spilled PCB fluid. The absorbent material and the contaminated soil are dug up and placed in an approved container. When the cleanup is completed, all contaminated clothing and rags are also disposed of as required. As we've seen, the actual maintenance to a capacitor bank is really not very difficult. It includes routine inspections and cleaning and replacing fuses and capacitors. However, you generally need to observe more safety precautions when working with a substation capacitor bank than for any other substation equipment. Aside from properly clearing and grounding the bank, you also must short capacitors that have blown fuses or that are damaged. You must exercise caution when working with bulged capacitors, and you need to observe the appropriate precautions when working with damaged capacitors that may contain PCBs. Now, aside from routine maintenance, capacitor bank failures can sometimes be avoided by testing individual capacitors. In the next part of this program, we'll look at capacitor bank testing. Substation capacitors are not typically tested on a routine basis. Usually they're only tested when there are indications of trouble, such as blown fuses, or if the capacitors have been exposed to unusual conditions, such as severe weather. In general, there are three parts of a capacitor that can go bad. These are the internal bleed resistor, the capacitor insulators, and the internal capacitive elements. In this part of the program, we'll look at how to test the bleed resistor and the insulators. Before going near a capacitor to test it, first make sure that it has been properly shorted. To test the internal bleed resistor, its resistance is measured, generally by using a multimeter or a megometer. Here, a worker is using a multimeter. The test is set up by connecting one lead of the multimeter to the neutral terminal of the capacitor, and the other lead to the normally hot terminal of the capacitor. Then the short across the capacitor is removed, and the meter is adjusted to the appropriate setting to apply voltage to the capacitor. The resistance indication on the multimeter is allowed to stabilize. Then the resistance reading is documented. Some companies require that the reading be taken at a prescribed time after voltage is applied. This results in readings that can be compared over time and that can be compared with readings for other capacitors in the bank. The resistance reading can also be checked against the manufacturer's rated resistance for the capacitor. If the resistance is not within an allowable range, the capacitor is typically replaced. After the test is completed, the multimeter can be turned off. The capacitor should be allowed to discharge through the bleed resistor for several minutes before the short is reinstalled on the capacitor. Finally, the multimeter is removed from the unit. When a bleed resistor is tested using a megohm meter, the megohm meter is connected the way the multimeter was connected. One lead is connected to the neutral terminal of the capacitor, and the other lead is connected to the normally hot terminal. Then the short is removed from the capacitor. The nameplate of the capacitor is checked to determine the unit's voltage rating. The megohm meter is turned on to apply voltage to the capacitor and get a resistance indication on the meter. The voltage is increased a step at a time up to the voltage recommended by company procedures, but without exceeding the rated voltage of the capacitor. With each voltage adjustment, the resistance indication is allowed to stabilize. After the last voltage adjustment, the indicated resistance can be compared to the rated resistance for the capacitor. The indicated resistance is documented. When the test is completed, the megohm meter is turned off. The capacitor is allowed to discharge for several minutes before the short is reconnected to the capacitor and the megometer leads are disconnected. If the capacitor has two bushings, the megohm meter can also be used to test the ability of the capacitor's insulators to insulate conductors from ground. The insulators include the bushings, the insulating oil, and internal insulating paper or film. The test measures resistance from each terminal to the case of the capacitor. The reason this test is only done on two bushing capacitors is because on a one bushing capacitor, the neutral is connected to the case, and so resistance from the terminal to the case would include the bleed resistor. The test is fairly easy to do. The short across the capacitor terminals is kept on. This keeps the capacitor discharged and makes it possible to test the insulation of the capacitor from both terminals to ground. In addition, both terminals of the capacitor are disconnected from the bank so that only the insulators for that capacitor are tested. As a precaution, one terminal is temporarily grounded until the test is started. One lead of the megometer is connected to the capacitor tank. The other lead is connected to one of the capacitor terminals. Then, just prior to performing the test, the temporary ground is removed. With the voltage range of the megometer set below the rated voltage of the capacitor, the megometer is turned on to apply voltage to the capacitor. The resistance indication is allowed to stabilize. Then it is documented. If the resistance is not within an allowable range, the capacitor is replaced. When the test is done, the megometer is turned off. The temporary ground is reconnected, and the leads of the megometer are removed from the capacitor. If testing the bleed resistor and the insulators of a capacitor turn up no problems with the capacitor, at least one other test can be made. This test is a capacitance check, a test to determine the ability of a capacitor to store a charge. We'll look at capacitance testing in the next part of this program. The purpose of testing the capacitance of a capacitor is to determine if the unit's capacitive elements are partially failed, short-circuited, or open-circuited. We're going to look at three common methods of capacitance testing. Typically, capacitance is checked by applying voltage to and testing one capacitor at a time. For this check, the unit is disconnected from the bank. As a precaution, the terminals are shorted and grounded until the test is performed. The instruments used for this check include an ammeter, a variable voltage supply, and a voltmeter. For a capacitor with two bushings, the ammeter is connected first to a suitable ground, and then to either terminal. Here it's connected to the neutral terminal. For a capacitor with one bushing, the ammeter would be connected to the normally hot terminal. The reason is that here, the neutral terminal is connected to the capacitor tank, and the tank is connected through the support structure to the other capacitors in the tier. Both the voltage supply and the voltmeter are also connected first to a suitable ground, and then to the normally hot terminal of the capacitor. After the instruments are connected, the short is removed from the capacitor and the temporary ground is taken off. The voltage supply is energized. Then it's slowly adjusted until the voltmeter indicates that 120 volts is being applied to the hot terminal of the capacitor. With 120 volts applied to the hot terminal of the capacitor, the ammeter will indicate any current that flows through the capacitor to the neutral terminal. The current will usually read less than 1 amp. Using a conversion chart, the current reading can be converted to capacitance and compared to the manufacturer's acceptable range. If the capacitance is not within the acceptable range, the capacitor should be replaced. With the method of capacitance testing that we just looked at, each unit to be tested must be disconnected from the bank and hooked up to a voltage supply. An ammeter is used to take a current reading, which is then converted to capacitance. Another way of checking capacitance is with a handheld capacitance checker. For this test, only one terminal of the capacitor needs to be disconnected from the bank. It can be either terminal. Here, the normally hot terminal has been disconnected. The terminals have been shorted for safety. One lead of a handheld or portable capacitance checker is connected to the neutral terminal of the capacitor first. Then the other lead is connected to the normally hot terminal. The short is removed, and the capacitance checker is turned on to apply a small voltage to the capacitor. The capacitance checker measures the capacitance directly. This figure is documented. Checking capacitance with a handheld checker is easier and quicker than using a variable voltage supply with a voltmeter and an ammeter, but it still involves disconnecting part of the capacitor and applying voltage to one capacitor at a time. There is a third method of checking capacitance that doesn't require disconnecting each unit and applying voltage one unit at a time. With this approach, a test device is used to apply voltage to an entire section of capacitors. The capacitors are not disconnected from the bank. To perform the check, the grounded source conductor to the capacitor bank section is disconnected. One lead of the test device is connected to the neutral side of the bank. Here, the connection is made to a conductor that connects the neutral frames of the bank. The other lead is connected to the normally hot side of the bank. Here, the connection is made to the normally hot bus of the bank. After the test leads are connected, the voltage source is adjusted until the capacitor bank section is energized at the voltage specified by the manufacturer of the test equipment. Then, using a shotgun stick, a clamp probe is placed around the fuse of a capacitor to measure the current drawn by that capacitor. The current reading is allowed to stabilize. Then it is recorded. The clamp probe is moved to the next capacitor, and the current drawn by that capacitor is measured and recorded. This is repeated until the current drawn by each capacitor in the section is measured and recorded. The current measured for each capacitor is compared with the acceptable range provided by the manufacturer. Any capacitor with a current reading either above or below the range should be replaced. Whenever a capacitor or a group of capacitors in a bank is replaced, the balance of the bank has to be checked. What this means is that the total capacitance in each phase of the capacitor bank should be equal to the total capacitance in each of the other two phases, within a tolerance specified by the manufacturer or company standards. To check the balance of a capacitor bank, measure the current of each unit in a given phase of the bank. All the currents for the phase are added together to get the total current for the phase. The currents are measured and totaled for each of the other two phases in the bank. The total currents for each of the three phases should be equal within the manufacturer's or company's allowed tolerance. If the phases aren't balanced, capacitors with high current measurements in one phase are exchanged with capacitors with low current measurements in the other phases until the phases are balanced. Now, up to this point, we've looked at the function of substation capacitors and shunt reactors and how they're used to improve power factor. We've also looked at clearing, maintaining, and testing capacitor banks. Reactors require occasional maintenance and testing too. In the next part of this program, we'll look at several different substation reactors. We'll look at how they're cleared, and we'll look at some of the maintenance and testing they require. There are two basic types of substation shunt reactors. One is oil-insulated. An oil-insulated shunt reactor can look a lot like a substation power transformer. One basic difference between a power transformer and an oil-insulated shunt reactor is that the shunt reactor has three-phase circuit connections to only one set of bushings. The other set of bushings is connected to ground. The other type of shunt reactor is an air core shunt reactor. This type of shunt reactor is an exposed coil that is mounted on insulators. A source conductor is connected to one end of each single-phase reactor coil. The other end of each coil is connected to ground. Here, the connection to ground is through a bus bar, a vacuum switch, and a flexible ground cable. Both oil-insulated and air core shunt reactors serve the same function. They improve power factor by offsetting excessive demand for capacitive power. In general, shunt reactors require very little maintenance. Typically, all that's done on a routine basis is a visual inspection while the reactor remains energized. Here, a worker is going to inspect an oil-insulated shunt reactor. An inspection generally includes recording various indicator readings and checking the condition of the reactor. An important first step is to identify the reactor that is being inspected. After that, readings and conditions are often noted as you walk around the reactor. Oil-insulated reactors may have temperature gauges from which readings are recorded. By regularly recording various reactor conditions, a history is developed. This history may be useful in determining when and if maintenance is needed. Bushings are routinely checked for cracks or other signs of damage that can reduce its ability to insulate. Damaged bushings should be repaired as soon as possible. The reactor grounds are inspected to ensure that there are no breaks or mechanical separations. The ground connections are checked to make sure that they have not corroded or worked loose. Corrosion or other signs of deterioration or damage should be noted for possible maintenance. Loose connections may be tightened on the spot. Any device that contains oil may develop leaks. Some common places where leaks occur include welded or bolted seams and around valves. Any leak or sign of a leak should be noted so it can be monitored or scheduled for maintenance. If enough oil leaks out of a reactor, the reactor could be left without adequate insulation and could fail. For this reason, an inspection of an oil-insulated reactor should include checking the oil level. The oil level will vary some with changes in outside temperature and with changes in the load. In general, if the level falls outside of this band, the cause should be investigated and corrected. Another indicator that is checked is the flag on a pressure relief device. If arcing occurs inside the reactor, gas is created that increases pressure inside the reactor. If the pressure increases enough, the relief device will vent the gas to atmosphere. When the device operates, a flag will pop up. A raised flag on the relief device should be noted so that if there is a problem with pressure, it can be corrected. An oil-insulated reactor may also have a gas detector relay. The relay measures gas in the reactor and triggers an alarm when the gas volume reaches a predetermined value. Gas volume is noted during the inspection. Finally, the reactor's control cabinet is inspected. The cabinet houses protective relays and alarms for the reactor. The control cabinet should be watertight to prevent moisture from causing shorts. If there are any signs of leaking, the cause should be identified and corrected. It's also good to keep the cabinet clean. Dirt, leaves, wasp nests, and other foreign objects could affect the operation of the control equipment. Inspecting an oil-insulated reactor is similar to inspecting a power transformer or an oil circuit breaker. An air core reactor is a little different because it's much simpler than an oil-insulated reactor. But it's just as important to routinely inspect this type of reactor as well. Normally, a visual inspection is all that is required. Care should be taken to stay a safe distance from an air core shunt reactor while it is energized. The main visual checks include the support insulators and the winding shims. The support insulators are checked for breaks, cracks, or chips that may weaken their support of the reactor and allow current to leak to ground. The winding shims are also checked for cracks or chips that may allow current to arc across windings. Sometimes current leakage or arcing is indicated by buzzing noises at the reactor, even if it isn't visible. Current leakage to ground or arcing across windings can create enough heat to cause further damage to the reactor and lead to its failure. If you suspect such problems, it may be necessary to take the reactor out of service and test the reactor insulators. The principles of taking a reactor out of service are the same as for clearing and grounding any other device in a substation. Permission and specific instructions are obtained for de-energizing the reactor and isolating it from the circuit. Here, an oil-insulated reactor is both de-energized and isolated by opening a motor-operated switch. After the reactor has been properly de-energized and isolated, it is tested for dead. Finally, it is grounded. Here, the shunt reactor is grounded by closing a set of ground switches. With the reactor properly grounded, a couple of very simple maintenance tasks can be performed. One task for an oil-insulated reactor is to clean and inspect the bushings. For an air core reactor, the support insulators are cleaned, and the windings and winding shims can be more closely inspected. Finally, the insulators for the reactors can be tested using a megometer. The test is very similar for both the oil-filled shunt reactor and the air core shunt reactor, so we'll watch how the test is performed on just one of them. On a shunt reactor, the insulation is tested one phase at a time. So for this reactor, a bar that ties all three neutral terminals together must be removed to isolate the three phases. As a safety precaution, each of the neutral terminals is individually grounded until the test is performed. Next, the neutral and source terminals for each phase of the reactor are shorted together, and the source leads are disconnected from the reactor source terminals. Now, the megometer can be connected to one phase of the reactor to test its insulators for that phase. The ground lead of the megometer is connected to a station ground. Here, station ground is the ground bus that was disconnected from the neutral terminals of the reactor. The voltage lead of the megometer is connected to one of the neutral terminals. Then the ground is removed from the neutral terminal. So now the megometer is connected to station ground and to the shorted terminals of one-phase coil of the reactor. The voltage setting of the megometer is adjusted to a value below the rated voltage of the reactor. The megometer is energized to apply a DC voltage to the reactor. A caution is needed here. The megometer provides enough DC voltage to the reactor to cause a serious shock. For your safety, stay away from the reactor terminals while the test is being performed. After the megometer is turned on, the resistance indication is allowed to stabilize. Then the resistance reading is documented. To test the insulators for the next phase of the reactor, the megometer is turned off. The ground is reconnected from station ground to the neutral terminal, and the voltage lead of the megometer is moved to the neutral terminal for the next phase to be tested. When insulation tests indicate a problem with a reactor's insulation, the reactor is either repaired or replaced. In general, with proper inspections, maintenance, and testing, reactors can stay in service for many years without experiencing a significant problem. Now, the reactors that we've looked at so far have been shunt reactors, and as we learned, their function is to offset excessive demand for capacitive power. Substations may include another type of reactor called series reactors. They look very similar to an air core shunt reactor, but they serve a completely different purpose. We'll look at series reactors when we continue. A series reactor can sometimes look very much like an air core shunt reactor. A typical series reactor is an exposed coil. The turns of the coil are separated and supported by a non-reinforced concrete or epoxy frame. One of the main physical differences between a series reactor and an air core shunt reactor is that a series reactor is connected in series with a circuit. A series reactor is also known as a current-limiting reactor. This name suggests the function of the reactor, which is to limit current. A graphic demonstration will help to show how a series reactor works. The coil construction of a reactor causes voltage to be induced from any given coil to adjacent coils. This induced voltage opposes and inhibits current flow through the reactor. As source current to the reactor increases, induction in the coils increases, further inhibiting current flow through the reactor. Now, during normal system conditions, the current flow that is inhibited by the reactor is minimal. Where the reactor comes into play is when current increases rapidly, for example, because of a fault in the system, or switching surges, or surges caused by lightning strikes. In cases like these, a series reactor is quite effective at limiting current flow. There are a couple of advantages to limiting current flow with a series reactor. One advantage is that it helps to protect other system equipment from excessive current. The other advantage is that a series reactor reduces the fault interrupting capacity required by associated circuit breakers. This means smaller circuit breakers can be used to isolate faults when a reactor is in series with the breaker. For example, these three single-phase reactors are connected in series with the load side of a three-phase power transformer. The reactors are in line between the power transformer and feeder circuit breakers, which are located behind this capacitor bank. A simplified illustration will help us see the relationship of the components and understand what these series reactors do. This illustration includes a power transformer, three single-phase series reactors, and a three-phase feeder breaker. Current flows from the transformer through the reactors and through the circuit breaker to the load. To better understand the function of the reactors, let's first see what a feeder fault can do if the reactors aren't there. If a fault occurs out on the feeder, the fault may draw excessive current through the power transformer, the feeder circuit breaker, and the feeder circuit to the fault. Such excessive fault current can damage the feeder and equipment on the feeder, and possibly the transformer. In addition, the circuit breaker will have to be large enough to have the capacity to interrupt the high fault current. Now let's see what would happen with the series reactors back in the circuit. When a fault occurs on the feeder, fault current increases induction in the reactors. The induction opposes and limits the flow of fault current to the feeder. In this way, it protects the feeder and feeder equipment from high fault current. To some degree, it also protects the power transformer from high fault current. And because it limits the flow of fault current through the circuit breaker can be smaller and have a lower fault interrupting capacity. Series reactors, like air core shunt reactors, require very little maintenance. In general, any maintenance that might be done is typically performed when the device that the reactor is protecting is serviced. The principles of de-energizing and isolating a series reactor are the same as they are for any other device. Switches are open to electrically and physically separate the reactor from its circuit. To de-energize and isolate these reactors, first, a three-phase feeder breaker is opened. Opening the breaker removes the load from the circuit that the reactors are in. Then, disconnects are opened at the breaker to provide a physical break in the circuit between the reactors and the load. Finally, motor-operated switches are opened to provide a physical break in the circuit between the reactors and the source. After the reactors are safely de-energized and isolated, they're tested for dead and grounded. Be sure to follow your company's safety procedures both when testing a reactor for dead and when grounding it. With the reactor grounded, it can be safely checked for damage or signs of problems. The connections to the reactor are checked to make sure they're secure and in good condition. The coils are inspected for signs of arcing, accumulations of debris between the coils, and other unusual conditions. The coil supports are checked for cracks or chips that may allow current to arc across the coils. If arcing is evident, or if the coils or supports are damaged, the reactor may need to be taken down and overhauled or replaced. The insulators are checked for cracks, breaks, and signs of tracking. If an insulator is damaged, it may need to be replaced. To summarize, series reactors are similar in appearance to air core shunt reactors, but they perform a very different function. They limit current flow. Maintenance is typically performed when the device that the reactor is protecting is serviced, and even then, maintenance is limited to inspection and cleaning. Throughout this program, we've looked at the functions of substation capacitors and reactors, what maintenance and testing they require, and what safety precautions are necessary when working with them. Capacitor banks are fairly common in substations, so if you work in substations on a regular basis, you'll eventually work on them. Shunt reactors are becoming more common where long, high-voltage transmission lines are installed, and series reactors are also showing up in more and more places. What you learned here will help you understand the function of these devices and how to safely maintain and test them.